Okay, we'll go ahead and get started. Can you see my slide and hear me?
Yes.
Thank you. So what we're going to do today is we're going to pick up where we left off with chapter 6, and we'll end in about 30 minutes, and then you'll be able to take the quiz for chapter 5. All right, so on Monday, we started talking a little bit about Bohr and his model that he based on the initial work that Planck did. And so he was studying the electron in a hydrogen atom and said that the orbits had certain radii, and that corresponded to specific energy. And we talked a little bit about the energy transitions and how they're set amounts of energy and things like that. So we also talked about how you have these allowed energy states, and that energy is emitted or absorbed only when the electron has energy that corresponds to what that value is, and that photon energy is calculated with the formula down at the bottom here. Energy equals Planck's constant times velocity. So you can't just have more intense energy. It has to be at the right frequency in order to have the transition occur, whether either absorbing or emitting a photon. In that Bohr model, we said that electrons that are in the lowest energy state are in what we call the ground state. And in this diagram, that's an N equals 1. And we'll learn in a moment what that N stands for. Any energy level higher is called an excited state, and that can be 2, 3, 4, whatever. And we can do some calculations around these energy levels using the constant and then the difference in the quantum numbers. So if the delta E is positive, then that means energy is absorbed. So in other words, the photon is absorbed. And if delta E is negative, that means energy is released. So in other words, the photon is emitted. The energy of the photon must equal the energy between the two states. That's the key takeaway on this. If the energy doesn't match what the energy difference is between, in this case, N1 and N2, then you don't get a transition. You don't get a transition up to N2 if the photon's absorbed, and you don't get a transition from N2 to N1 for the photon emitted if that energy doesn't match. So in other words, the frequency doesn't match. So like a lot of these things that in chemistry, people get ideas, they test them out, it looks like it kind of works, and then they start expanding it to other things, and they start to see some of the problems with it. And that happened with Bohr and his model. He was studying hydrogen, which is the simplest thing he could study. And unfortunately, when he started applying it to other atoms and other molecules, then it didn't hold up anymore. And so that circular motion that he proposed turned out to not be correct, because as it was studied more, it turns out that the motion is more of a wave-like motion, and Bohr's model didn't predict that. But there were a few things that came out of the Bohr model that are still useful and are used today. One is that the electrons exist only in discrete energy levels. And that's where the quantum numbers we'll talk about in a few moments come into play. And also, energy is involved with the transition of an electron from one level to another. So electrons have discrete energy levels, That's the quantum number stuff, which we'll learn about in a few moments. And then also when you have transitions, when electron transitions occur, discrete energy is involved in that. So de Broglie theorized that light should have wave-like properties. And he was able to show that there's a relationship between mass and wavelength. And that's the formula we see here. Wavelength is equal to Planck's constant divided by mass times velocity. And then mass times velocity, that's known as momentum. So what we see is that we have a relationship here that shows wavelength and mass are inversely proportional. So there's some homework problems on this first part. I'm not going to go over those today. I prefer that you have a chance to look them over and try some of them. And so on Monday, I'll go over some of this stuff. So for now, I'm just going to continue on with the lecture part. So a guy named Heisenberg came up with something called the Heisenberg uncertainty principle. And what that did, it showed that the more precisely that the momentum of a particle is known, the less precisely its position is known. And so this led to the Schrödinger equation and the whole field of quantum mechanics. So Schrödinger developed math around demonstrating that electrons have and light have wave and particle nature. And so that's the field of quantum mechanics. We'll touch on that a little bit in this class. If you take physical chemistry later on, you'll get more of it and you'll actually see the math in more detail. But basically what quantum mechanics does is it allows you to give prediction of where the electrons are. And this figure on the right-hand side of the slide with the XYZ coordinates is a dot density diagram. And what that shows you is the likelihood of where the electron is located. So in this case, for this example, it's right around the 0 point of the XYZ axes, but it also expands out. It's less likely out there, lower probability, but it is a probability. If you solve the Schrödinger's wave equation for hydrogen, then you get wave functions for that electron. The square of the wave function, and that's this little pitchfork looking symbol, squared, or psi is the correct name. That's the electron density, or as I was saying, the probability of where an electron is at any given time. And so the darker it is, the higher the electron density, the higher the probability that you'll find the electron in that location. So that leads us to quantum numbers. So solving that wave equation gives you a set of wave functions, which we call orbitals, and their corresponding energy. Each orbital describes a spatial distribution of electron density, and the orbital is described by a set of 3 quantum numbers. And so we're gonna discuss what those 3 quantum numbers are. The first one is the principal quantum number, N. And the principal quantum number describes the energy level on which the orbital is at. And so the values of N are always integers, and they're greater than or equal to 1. As N increases, so in other words, as you go from N equals 1 to 2 to 3 and so forth, the orbital becomes larger and the electron spends more time farther from the nucleus. The electron has higher energy and is less tightly bound for these higher N values. The next quantum number is the angular momentum quantum number, designated as L. And this tells us what the shape of the orbital is. So principal quantum number tells us basically how closely it's bound, and it describes the energy level. The angular momentum quantum number tells us the shape of the orbital. And the allowed values for this are, once again, integers, and it goes from 0 to n minus 1. So if n is 1, then you would just have 0. If it's 2, you'd have 0 and 1, and so forth. The thing that's a bit different about this quantum number is, even though we have numerical values, we have these integers, we don't use those numbers when we describe it. We use letters instead. So you see in the table below, we have where if the value of L is 0, then we use an S. If it's 1, we use a P, 2, D, 3, F. So when we, in a little bit, when we see the nomenclature for this type of stuff, we won't use those numbers, we'll use those letters. The third quantum number is the magnetic quantum number, and that's M sub L. And this describes the three-dimensional orientation of the orbital. So the allowed values, once again, are integers, and they range from minus L to plus L, including 0. So in other words, for the S orbital, we have 1 number for the magnetic quantum number. For the P, we have 3 orbitals. D, we have 5, 7, F, and on down the line. The shell with principal quantum number n consists of exactly n subshells. And then each subshell consists of a specific number of orbitals. The total number of orbitals in a shell is n squared, where n's that principal quantum number of the shell. So if it's 1, it's 1. If it's 2, it's 4. If it's 3, it's 9, and so forth. Okay, I think this table does a good job of kind of piecing together all the stuff that I've been talking about. And to me, it always sounds a little abstract till I see something like this. So once again, orbitals with the same value of n form an electron shell. Different orbital types within a shell are called subshells. So let's look at this relationship between n, L, and m sub L. And so we see in the table that if n equals 1, then the possible values of L, it's just the 0, because remember, n minus 1, including 0, so we have 0. And so that subshell designation would be 1s. The possible values for m sub L would be 0. So now the number of orbitals in the subshell is 1, and the total number of orbitals is 1. If we go up to 2, n equals 2 for the principal quantum number, then we have that 2s, just as we did with the 1s. So L is 0. We have the subshell designation of 2s. ML is 0. 1 number of orbitals in the subshell. But now we have a second value of L, the 1, and so now we have a 2p subshell designation. And with 2p, now we have 0, 1, and minus 1. And so now we have 3 orbitals in the subshell. And so we have the 3 from the 2p subshell, we have the 1 from the 2s for a total of 4. And then we go on to n equals 3. Now with n equals 3, that gives us 3 values for L, 0, 1, and 2. So we have 0 and 1 similar to what we saw previously with 3s and 3p, but now we have the 3D subshell as well. And with that, we have 5 possible values for ML: 2, 1, 0, -1, and -2. So we have 5 orbitals in that subshell from the 3D. We have 3 from the 3P, and we have 1 from the 3S for a total of 9. And then finally, for the n equals 4, now we have 4 values for L, 0, 1, 2, and 3, and we add that 4F subshell. And with 4F, we have 3, 2, 1, 0, -1, -2, -3. So we have 7 orbitals in the subshell there. So we add all those up, 1, 3, 5, and 7, and we have 16 total. So this is how we use these quantum numbers to figure out how many orbitals are in a shell, what's the configuration, things like that. So let's take a look at a little bit at the orbitals to see what they look like. So let's start with the s orbital. And if we look at that electron density model on the left, we see that it looks kind of like a sphere. And so the contour models on the right make that a little bit clearer to see that. And what we see also is as we go up in principal quantum number from 1, 2, and 3, we see that the sphere gets bigger. So the other thing that we have about the s orbitals is that if we look at these radial probability function plots at the bottom, the y-axis is the probability. So that means how likely are you to find the electrons there. And then the x-axis is the distance from the nucleus. We see that for the 1s, we're likely to find the electrons pretty close to the nucleus. As we go to 2s, we see two nodes now where we see some likelihood close, then it dips down to a little bit of likelihood, but the more probable distance is a little further out. And then same thing with 3s. As we get to these bigger orbitals, in other words, the increase in the principal quantum number, we see that the most probable distance to find the electrons gets further away from the nucleus. And what this is telling us is that things are just spreading out more so. Okay, let's look at the p orbitals. So we know there are 3 p orbitals, and they start at the n equals 2 shell. And what we see in that is that they have 2 lobes with a node in between. So a node, remember, is that where you don't have very likely to find the electron there. So you're seeing the orientation of the 3p orbitals around the x, y, and z axes. So we see the z-axis one, that's the one that's going up and down. The x-axis and y-axis, the x is going kind of to the left and the y-axis is going kind of to the right. And so, but they all have the 2 lobes in common, and that's what the p orbital looks like. Then the next one is the d orbital. We know from the quantum numbers that we have 5 d orbitals, and the d orbitals have 4 lobes, at least 4 of the 5 do. So we have 4 of them that have 4 lobes, and we see those displayed here in the planes along the x-axis, the y-axis, the z-axis, things like that. And then we have one where the lobes are in between as well. And then the final one is that last one that has two lobes, and then it has kind of the donut looking thing around the center. So 5 orbitals, 4 of them have the 4 lobes, and then 1 of them has the 2 lobes with the donut looking center. And then finally, there's the F orbitals. We're not really going to talk about those. Those shapes are kind of complicated, and so we're not going to fool with those in this class. Okay, so let's talk a little bit about the energies of orbitals, looking just for now at hydrogen. So hydrogen, as we know, has 1 electron. It's a 1 electron atom. And so the orbitals on the same energy level have the same energy. And we call this degenerate orbitals. So in this diagram on the right, each of those little boxes represents an orbital. And then each cluster of boxes represents a subshell, and then each kind of row across is a shell. So down at the bottom, we have 1s. So that's just 1 orbital there. We go up to n equals 2, that n equals 2 quantum number, principal quantum number. And we have 2 subshells, 2s and 2p, for a total of 4 orbitals, 1 in the 2s and 3 in the 2p. And then in n equals 3, we have 3 subshells, the 3s, the 3p, and the 3d. And if we add up all those orbitals, we have 9. So in this example with the hydrogen, we're saying that the 2s are all at the same energy, the 3s are all at the same energy. We see the energy going up as we go from 1s to 2 to 3. So that sounds pretty good. The problem is this really doesn't hold up for anything but hydrogen. When you get to elements that have more electrons and you get to compounds and things like this, you don't see this nice kind of what I would call stacking of the energy levels. What you see is something more along the lines of this. So as the number of electrons increases, you start to get repulsion between the electrons. Life's pretty simple when you just have 1 electron. Now you have more, and you have these different orbitals that are kind of conflicting with each other. So what this means is you have atoms, you have orbitals that have different energy levels. So in other words, they're not degenerate anymore. We see here in this example that the 2 and the 3 and the 4 shells don't have their subshells at the same energy level. Within the subshell, they're still degenerate, they're still the same. So in other words, if we look at the 3p, all 3 of those 3p's are still at the same level, but the 3p is different than the 3s or the 3d. We also start to see some overlap. So we start out at 1s, then we get to 2s, then we're 2p, we're going, okay, 3s, 3p, but now instead of 3d, we have 4s, then we have 3d, then we have 4p. So this is what we talk about when we talk about some of this overlap in energy. And so it gets a little more complicated as you start adding more and more electrons to sort through the energy levels. So we said there were 3 quantum numbers, and actually there are 4 quantum numbers. There's a 4th one called the spin quantum number, m sub s, and that describes the spin of an electron when it's placed in a magnetic field. And so the magnetic field affects its energy. And so this spin quantum number is either +0.5 or minus a half. Pauli came up with something called the Pauli exclusion principle. And what that says is that no two electrons in the same atom can have the same set of 4 quantum numbers. And so since they don't have the same quantum numbers, that means no two electrons in the same atom can have the exact same energy. So every electron in an atom must differ by at least one of the 4 quantum numbers, whether that's the N, the L, the M sub L, M sub S, doesn't matter, but there's got to be at least one of those that's different. And so no two electrons are the same is what it's saying within that atom. So the nomenclature that we use to talk about these electron configurations is what we're gonna go through a bit now. And so the way those electrons are distributed in the atom, that's the electron configuration, and there's certain ways that we represent that and write that. Remember that the most stable and lowest energy configuration is called the ground state. And so when we write this out, we have a number which tells us the energy level. So in this example down at the bottom, that's the 4. A letter denoting the type of orbital, that's the P. And then the superscript tells us how many electrons are present in those orbitals. And in this case, it's 5. So what this 4p5 tells us is that in that 4p level, in that p orbital, we have 5 electrons. So when we write stuff out like this, so here we have for lithium, which has 3 electrons. And so each of those boxes represents an orbital. So the first box represents 1s, the second box represents 2s. And to reflect the electrons that are present at each of those levels, we use this half arrow convention. And so you see one arrow going up, one arrow going down. The up and down represents the different spin. And when you do this, if you only have one electron present, like in the 2s, you always draw it with the arrow going up. That's just the convention that's used. Okay, we have something called Hund's rule, and this helps us figure out how to fill up the orbital diagrams when we're trying to figure out these electron configurations for an atom. And so Hund's rule says that when you're filling degenerate orbitals, the lowest energy is attained when the number of electrons having the same spin is maximized. So in other words, that means when you're filling a level, you first fill all one spin. So in other words, all of them going up. And then once you fill that, then you go and you start adding in the next set where you have some that go down. So before you start pairing up electrons, you have to fill up each of the orbitals before pairing them. So let's take a look at this example. So lithium's the one we just looked at briefly. So they had 3 electrons. So we'd fill 1s with 2 electrons. Then the third electron goes into the 2s for our orbital diagram. And if we look at our electron configuration, we see that's represented as 1s2, 2s1. So it tells us principal quantum number 1, s, 2 electrons in that. Then we go to 2, s, 1 electron in that. We go to beryllium the next with 4, and we see that here we fill up that 1s level, then we fill up the 2s level, and that gives us 1s2, 2s2. So it's telling us, once again, we have 2 electrons in the 1s and 2 electrons in the 2s. Let's skip down to carbon at 6. So we have 6, so we fill up the 1s, we fill up the 2s, then we start filling up the 2p. And notice also that the 2p energy is less than the 3s. So before we go to 3s, we have to be filling up the 2p. And so in this case, our electron configuration would be designated as 1s2, 2s2, 2p2. Nitrogen with 7, we fill that 1s and 2s, and then we put 1 electron in each of the 2p orbitals. And notice that we have them all drawn up. We're not pairing anything. We're not drawing any of them down. They're all pointing up. And we have 1s2, 2s2, 2p3. You go on to the others and you see as you go to the next ones, you start then pairing up those 2p's. And then finally, when you get the neon, you've got them all paired. Sodium is then when you go over and have filled up the 1s, 2s, 2p, and now you're starting in onto the 3s. When you have the same number of electrons in the outermost shell, the electrons in the outermost shell are called the valence electrons. And so when the inner electrons, which we call the core electrons, will be the same, and it's just those valence electrons that are different. And so what we do is a lot of times we can write kind of a shorter version of writing out the electron configuration by using the noble metal configuration. And so we'll have some examples of that. So argon is 18, and that ends period 3. So that noble gas, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Potassium, the next one, you might think it would be 3D, but the energy diagrams tell us that 4s is next. So here we see on the right-hand side the energy diagrams for these transition metals. And so as we get to the transition metals, we follow the filling of 4s by 3D. So there's some examples down on the bottom of that. So this is where we were talking earlier about you have overlap of these energy levels. And so you fill up the 1s, the 2s, the 2p, 3s, 3p, then you start going and filling up the 4s. And then after that, the 3D. All right, I think I'm going to stop there and let you start with the quiz unless anyone has any questions. Okay, then let's go ahead and start the quiz, and then we'll pick up with this on Monday.